The next speaker is Rachid Guerraoui. He is a professor at EPFL, and he's worked on anything that exists in distributed computing. He was the most requested senior in the DISC senior junior meetups. I'm not sure he knows that. And he's going to talk about how Bitcoin is an easy problem. Maybe it doesn't even need consensus.
Thank you for inviting me. It's a pleasure for me to talk to the W3 Foundation and your guests and participants. I have to confess that I heard about the W3 Foundation, but I didn't know exactly what it is doing. So maybe I will eventually know now. And I guess you have to do with the blockchain systems or protocols. And this is what my talk is going to be. And the title of this talk is the following: the payment problem is easy. And this is what I'm trying to share with you as a piece of information. And I also want to share with you another piece of information, which is you might feel that you would lose time or waste time by going back to the principles and sometimes even to the theory of distributed computing. But I believe that at the end of the day, you actually gain time and not waste time. And this is the second message I want to convey. The first message is that the payment problem is easy. The second message is that you should spend some time doing theory. Okay, so 3 years ago, I think I got interested into what I call the Bitcoin problem. I will explain what I mean. People were talking about the Bitcoin problem, especially Maurice Herlihy, a friend of mine, who started talking to me about the problem. He's a theoretician and practitioner, and gave me some insight about. Of course, I've seen papers, I heard about the Bitcoin, but then I decided to go and read the actual original paper of Nakamoto, which is considered to be the foundational paper. And what the paper does, in my opinion, is that it does two things. Indeed, it presents the protocol, the Bitcoin protocol that people implemented, got inspired from, changed, and so forth. But also it does something very fundamental in my opinion, which is it defines a problem. And the problem is what I call the payment problem or the Bitcoin problem. In fact, in the paper, it's called the double spending problem. And the problem is defined quite precisely. And from there, we started, I and some students and colleagues and former students, trying to really understand the problem without getting, let's say, polluted not in the bad sense, polluted by the protocols. We just try to focus on the problem and understand what the problem was. And we asked the question whether the problem was as hard as people claimed it to be, because the protocols that were implemented, I mean, thousands of them, looked very complicated to us. And indeed, many of them worked. But if I look today at the situation of, or even 2 or 3 years ago, the situation of even very serious startups and companies implementing, even big companies implementing Bitcoin protocols or blockchain protocols implementing, solving the problem, most of them were basically struggling to verify the correctness of their protocol. So today, initially they hired distributed computing people and crypto people, but later on, I have seen them hiring a lot of verification people because they wanted to make sure that the protocol is correct, which makes sense because the protocol was supposed to be doing serious stuff. Money is very serious. So they had to prove that the protocol is correct. And in many cases, it turned out to be a nightmare. I take the example of Definity or Interchain or others. I mean, they do spend a lot of time and energy. These are all smart people trying to prove that, convince themselves that the protocol is correct. And I believe the reason they do that is that because they're solving a problem that is hard. And the claim is that the problem is not hard. You don't need a difficult protocol because the problem is not hard. And we believe that our job as a computer scientist is to try to simplify. And this is what we have been doing for the last 3 or 4 years with students, former students and colleagues, is to basically study the problem. And we believe that we came to the conclusion that the protocols do not need to be as complicated as they are today. Okay. When you do theory, you try to classify. I'm mainly a theoretician, but I got interested in practice, and I hire practical students, and I try to learn what they do. But my background is mainly theoretical. When you do theory, you try to classify, and usually you try to classify into two sets. Once you classify into two sets, you go into subsets. I will go into that. So the world, you have two kinds of people: those with loaded guns, easy life, and those who dig. And in the blockchain world, digging has a precise meaning. So if you look at the classical way we studied, or you studied computer science, the world is divided into two categories, P and NP. I hope you all remember this classification. When you ask, give me two numbers such that their product is 91, this is a difficult problem. It's not easy to solve. You have to think a lot to find them. This is NP. If I tell you multiply 7 by 13, this is an easy problem because you immediately multiply and then you get actually 91. So this is P. So we know in the classical world of computing that there are difficult problems and easy problems. What we mean by difficult typically is the solutions are very expensive. They are very expensive in the number of instructions. Easy problems are not very expensive. But now when we go to distributed computing, what is hard and what is easy? The classification P versus NP is actually the classification in classical centralized computing. When you go to distributed computing, I do claim that the two categories are whether the problem is asynchronous or synchronous. What I call an asynchronous problem, or let me start by the synchronous. What I call a synchronous problem is a problem that requires nodes to synchronize. They need to solve some kind of consensus or agreement. And this is hard because sometimes it's impossible. And when it's possible, it's expensive. If you really look at the literature of distributed computing, problems that require a consensus are impossible if you don't make synchrony assumption. If you make synchrony assumption, they become possible, but you can actually translate the impossibility in the asynchronous world into lower bounds in communication. So let me summarize. Synchronous problems are problems that require consensus, and they are difficult, sometimes impossible, sometimes expensive. In contrast, you have problems that I call asynchronous, like sending a message is an asynchronous problem. You don't need to agree with anyone, you just send a message. Broadcast is also an easy problem. And the question we asked is payment an asynchronous or asynchronous problem? Of course, if you look at 3 years ago, when we looked at the papers and the systems that were implemented, it looked to us as if the problem was synchronous because everybody was basically implementing some sort of consensus. So it looked as if the problem was difficult, and therefore it's not surprising to see very sophisticated protocols, very complicated ideas, tens of thousands of lines of code. But was that really necessary? Okay. A big scientist in distributed computing, Tyler Lannister, said, if to understand the distributed computing problem, bring it to shared memory. I'm sure you all know Lannister. So he didn't really say that. Lannister is this Game of Thrones guy whom I like a lot. So he basically, I believe also that in order to really understand whether a problem is synchronous or asynchronous, you need to study it in shared memory. It's much easier. Why is that telling you anything? Because, okay, what I mean by shared memory is the following. In the blockchain area, typically we assume that we have the internet, large-scale system scaling in terms of geographically distant machines. And we have a very weird adversary which tries to control nodes and try to make them deviate from their protocol and even violate the double spending case or situation. In distributed computing, there is also another extreme world, which is the world of the infinitely small, which is called the shared memory world. In the infinitely big, processes communicate by exchanging messages. In the infinitely small, processes, they don't exchange messages. They read and write in shared memory. And here, we usually assume that the bad people, they're not really malicious. They are just sometimes slow, okay? I hope you are with me. In the world of distributed computing, there are these two extreme models: large scale in geographic sense, message passing, very, very weird adversary. And at the other extreme, there is this infinitely small with not a very bad adversary, although it can slow down processes. It turns out that this message passing model, where processes exchange messages with very bad adversary, and the shared memory model, where processes, they read and write in the shared memory, which is we typically call registers, these two models are equivalent. Okay, let me explain. Any problem you can solve in a message passing model, where by sending messages, you can also solve it in shared memory, and actually vice versa. So this is very important. I'm not saying that the complexity and the cost is going to be the same. I'm simply saying any problem you can solve it in one of these models. If you can phrase it precisely in the other model, you will be able to solve it, and vice versa. This is very important because when we want to study a problem, it's much easier to study that problem assuming a shared memory. But you will tell me, how can we even think about the payment problem in shared memory? Sure, you can think about it. I will explain that in a minute. So I'm not going to give you here this result. I think this is one of the fundamental results in distributed computing. It won the famous Dijkstra Award two or 3 years ago, basically saying how to emulate shared memory in message passing. Of course, you need an assumption that the number of correct nodes is some sort of a quorum. I'm not going to go into that, but intuitively, a quorum implements the abstraction of a shared memory. And once you have that, you can prove that the two problems are equivalent. The two models are equivalent. Okay, back to our big question. Is payment the problem defined by Nakamoto, whomever that means? Is that a hard or an easy problem? Easy in the distributed computing sense means asynchronous. We don't need to agree among processes. Is that the case? Okay, but I tried to convince you, even if I didn't go into the details, that it is sufficient to ask that question, assuming actually my own Macintosh that I'm using here with the few processors communicating by shared memory. I just need to address the question in this context. It turns out that when we try to study problems in shared memory, it is convenient to define the problems as object. Okay, because in the shared memory, we have objects like registers on which we can read and write. Sometimes we have queues, sometimes we have compare and swap, sometimes we have object in the classical object-oriented way. They have operations, and what we want to do in the shared memory is to have two properties when we implement these objects. We want the operations to be atomic, meaning everything happens as if the operation executes at a single point in time, and we want this implementation to be weight-free. If you want to think of the payment object, essentially atomicity tells you you should not have double spending, and weight freedom tells you whenever you want to send money to somebody, you should be able to do it. The system should be operating. I will explain that. Forget about the payment for a moment, and let's take an even simpler object. And you will see the relation with payment. Consider an object that is probably the simplest one can imagine besides reading and writing. Consider the object that does only counting. You can view that as a very simple form of payment. A counter object has two operations, increment and read. Okay? It has a state. The state is an integer x initialized to 0. When you increment, you simply add 1 to x. When you want to read, you return the value x. Okay, so assume I have this counter in my Macintosh, in my shared memory, and this counter is something that can be used by all the processes. They can read and write. And the question I'm asking here is implementing a counter easy or difficult? Do I need to solve agreement in order to do this or not? Or in other words, can I solve this? Can I implement this object completely asynchronously without making any assumption on the synchrony of the nodes? It turns out that yes, we can do that. And I really want you to understand the algorithm because it's a simple algorithm. I have n processes and they want to implement the abstraction of a counter. But of course, hardware doesn't give a counter. Hardware gives read-write registers. So can I implement the increment? Can I implement the increment and read operations of the counter using the registers asynchronously without waiting in an atomic and wait-free manner? Yes, I can do it. Okay, so let me go back here a minute. A naive way of doing it is to say, I will have one register per counter. Whenever I want to read the value of the counter, I will return the value of the register that is devoted, associated to that counter. Whenever I want to increment, I will just read the value of the register, add one, and write it back. It is easy to see that this implementation is not going to be atomic. Why? Because if I want to increment the counter, I read it, and I sleep for a while because it's an asynchronous world, and somebody else comes, writes, and then another process comes and writes again, and the third one comes and writes again, and then I wake up from my nap and I write on the counter, I will violate atomicity, okay? Because the counter should have value 3, and I will put it back to value 1, okay? I hope we are together. Very simple. A counter, if I implement it with one register, I won't have an atomic implementation. What I can do, however, is have n registers. So I can implement the counter with n registers if I have n processes. Whenever process I wants to, this is process I, wants to increment the counter, it goes to its register, it reads the value, it adds 1, and it writes back to that register. Every process has a register associated with it, okay? If I want to read, I sum the values of all the registers. I hope that you can see that I end up with a rather simple implementation that is wait-free, and that is atomic. Atomic in the sense that I can have several processes accessing the counter at the same time. They view the world as if they were alone. So meaning counter is a very simple object. The problem of implementing the counter is easy because I could implement it in an atomic way without using locks, without making any assumption on the synchrony of the processes. I really hope that I didn't lose you at this point. I hope that. So this is a counter. So conclusion, counter is an easy problem. Good. Now let's change the problem a little bit and add to this interface that I had, besides read and increment, now I have an operation decrement. And decrement, what it does is the opposite of incrementing if the value of the counter is strictly superior to 0. So if it's strictly superior to 0, then I decrement. Okay, so this is the new object I want to implement. I'm asking now, is this object also asynchronous? Is it easy to implement just like I did with the counter? It turns out that it's not. You can try, you can think at home whether you can do that, again, without using locks, without making any assumption on the synchrony of the processes. It turns out that this is a very difficult object to implement. And if you want to convince yourself that this is a difficult object to implement, what you can do is show that if you solve this counter problem, counter star, you can actually solve consensus, okay? So the way we actually show that a problem is difficult is that an object is difficult is by showing that with that object, you can implement consensus. I'm not going to recall what consensus is. I gathered from the previous talk that everybody knows what consensus is. If you have counter star, you can implement, and again, this is very simple. I'm sure everybody will understand. If I have counter star, I can implement consensus. How do I do that? Consensus is about proposing values, let's say integers, and deciding on a value. Every process who wants to solve the consensus problem with counter star proposes the value here, writes the value in a register devoted to that process, and then access the counter. We assume that the counter is initialized to 1, and we just have 2 processes. Okay, so we want Lefteris and I would like to solve consensus. Each of us has a register. I first write my value in the register. Weather is good in Lausanne. The weather is better in Lausanne. And he writes the weather is better in Greece. Okay, we want to see who is going to win, so to speak. We go to the counter and we decrement. Okay, but the counter has value 1. Intuitively, only one of us will be able to decrement. Okay, so if the result is okay for me, this means that I was able to decrement. I won. I return my value. Lausanne has a better weather. If I lose, I go to read what he wrote in his register, and what he wrote in his register is maybe Athens has a better weather. At the end of the day, we agree. We don't know in advance whether we are going to agree on his value or my value, but what breaks the tie is this counter. What I'm telling you here is that this counter star is very strong. It's very strong because if we have it, we can solve consensus with it. You cannot solve consensus with the counter without the star that I presented to you earlier. That's an easy problem. Counter star is a hard object because if I have it, I can solve consensus with it. I can solve consensus with it among 2 processes. Okay, you can actually try to solve consensus among 3 with Lefteris, Fateme, and myself, and you will realize that you cannot. You can only solve consensus with it among 2 processes. It turns out that we know that no algorithm can solve consensus among 2 processes using registers. Therefore, no algorithm can asynchronously implement the counter star, because if we could, then we could solve consensus. I hope I didn't lose you. Corollary, counter star is impossible. Why am I telling you all this? I'm telling you all this because I could give you, I hope, 2 examples, one easy problem, one easy object, counter, and one difficult one, hard, counter star. And there is actually a precise way, very precise, to actually go beyond the 2 classes. We have a class that is easy, counter, and we have another class that is hard. Class that is hard are made of objects that can implement consensus. Okay? Counter star can implement consensus among 2 processes. We say, and this is one of the most beautiful notions I ever met in my life as a researcher, we say that the consensus number of counter star is 2. Okay? Just like the Mendeleev table, which characterizes elements according to their atomic weight, you can characterize the power of problems in general and objects in particular with how many processes can we solve consensus with if we have that object. It turns out that counter star is exactly 2. And I will come back to this in the context of payment. Of course, I will not go into all the details, but let me now go back to payment. What is actually a payment object? The problem defined by Nakamoto, whomever that means. It's an object that has only one operation, pay with 3 parameters, A, B, X. And it consists of saying transfer amount X from A to B if there is enough money. Okay? It is important to notice that in the payment object of Nakamoto, only the owner of the account is able to give money, right? There is not such a thing as an account that is owned by several players, people, nodes in Nakamoto's paper. Only one owner. The question is, now that we have defined the payment problem of Nakamoto in the form of a shared object, is this object that I call PO, is it an asynchronous object? Can I implement it asynchronously just like I did it with the counter? Okay. And if I cannot do that, then what is the consensus number of this object? Is it 2, 3, 4? How hard it is? Okay, given the time, I'm not going to go into the details because I want you to go and read the papers. They are not very difficult, I promise. I will just give you the results, which I think you guessed, and I'm happy to discuss the papers later. I'm going to skip the algorithm, but it's not very difficult. I'm going to go directly to the conclusion. It turns out that the payment object resembles the counter object. It doesn't resemble the counter star. It resembles the counter. It can be implemented asynchronously. It does not need consensus. Its consensus number is 1, meaning it's the lowest. If you look at the hierarchy of the difficulty of object, this one has consensus number 1. Interestingly, if you assume, which is not done in Nakamoto's paper, that an account is owned by K nodes. So I have a bank account and I can withdraw money from it. My wife can, my 4 kids, yes, I have 4 kids. They all can. Then we define an object, what I call PO6. 6 people can withdraw money. We can prove that in that case, the consensus number of this object is exactly K. I hope that you can draw an analogy with the very notion of smart contracts, where you can have K people who can actually modify some states or withdraw money. So what did we do with this work? First, we have proven what I claimed, which I didn't show. We have proven in PODC 2019 that the consensus number of the payment object is 1. It's a very, very simple object, okay? Just like the counter. Simple does not mean that you don't need to think about it hard. It simply means you don't need consensus to do it. Okay, so this is our PODC 2019 paper. And then we implemented in shared memory what we said in the PODC paper. And then we moved to the message passing, and we actually translated back the result and the algorithm to message passing. And we actually have shown that the algorithm that results from that, a deterministic algorithm, it's much faster and 1 order of magnitude less lines of code than if you used consensus, no matter how you use it. I don't know of any very simple way to use consensus. And more, we also developed a randomized permissionless version of this algorithm, which was first shown in DISC 2019. And we are now in the process of implementing this randomized version. So this one is a deterministic one. This one is randomized. The deterministic is permissioned and the randomized is permissionless. So we have implemented these two, and both of them are actually message passing variants of the shared memory one. So if you want to know more, you can go to Cryptocurrencie at EPFL, and the papers are there. And if you if you even want to know more, you can download these books, or you can ask me. I can send you the books. They are behind me here. Thank you for your attention. And I go back to the original slide, which is the main claim. Feel free to ask me questions. And sorry for taking you far away from what you were discussing today, I guess.
Thank you very much, Rachid. So we have a question from Isaac, who asks that there are also other protocols such as Avalanche, Spectre, that do not use consensus. They use some idea of Byzantine broadcast. And their problem is that they lose liveness if some account owner tries to double spend. Basically, if there is a double spend, there is a misbehavior, the money is in flux, and we never say that's wrong. We actually will decide that that's wrong. Do you think there's something fundamental in there?
Yeah, I think there is something very fundamental there. The difference between Byzantine broadcast and terminating broadcast is exactly what Isaac, if I remember the name, is explaining. In this version of the problem that we also have been studying, if the source of a transfer is trying to double spend, and that source is bad, we don't decide. That is true. But we don't need to decide. We are not violating any property for any honest player. Of course, we are not catching the source of the double spending because we don't terminate the broadcast. If we require that we want to catch the source of a double spending, then the problem becomes harder. So the remark is very good.
I also have a question. So if we look into consistency models, we know that up to causal consistency, we don't need strong consistency. So if we try to implement something more than payments, like some kind of transactional model, do you think that there is a translation in there? Like if we have a smart contract and we want some data structures that are commutative, for example, will that be fine and not need consensus?
Yeah, a good question. So what I tried to say with that famous number K is that if you have a smart contract where you really want to have some sort of agreement, because you can have many smart contracts where you don't need to agree, but if you want to agree, then what our PODC paper shows is that if the smart contract is between K, you don't need, then the consensus number of the object is K, which exactly means you only need agreement between K people. You don't need all people in the world to know exactly whether you agreed and what you agreed upon. They might even have, and this is important, different perceptions on what you agreed on. Whereas if you have consensus in the classical sense, everybody has the same perception. My take is that you can go from payment to slightly more difficult problems where K people have to agree, but in that case, you only need consensus among K. People outside the contract can even have a completely different views of what you decide.
Thank you very much for the talk, Rachid.